Hi, today we are talking about a novel software communication solution for distributed systems called Native RPC. We'll be addressing some of the most basic communication needs of distributed systems, finding ways for the software processes to communicate across different environments and different programming languages. First, a few words about the space this solution lives in. In the past 3 to 4 decades, the software development field has produced many popular and widely adopted solutions. Many of these utilize a schema marked in green. Some emphasize the ability to be cross-platform, typically relying on a custom schema definition and code generation like gRPC and GraphQL. Others are more language-specific, declaring the schema inline or with some custom class annotations, typically on an end-to-end or endpoint-to-endpoint basis. Some solutions rely on fully dynamic payloads, payload validation, serialization, remapping, things like that. And of course, some of these concepts are bound to be highly relevant and important to some of us as developers, yet completely redundant and pointless to others. This raises a question. What is the next step in process-to-process communication? Is there a way to consolidate things to a single solution? Is anybody even working on a question posed in 1997 to Steve Jobs? See YouTube link for more info. And are we doomed to keep jumping from one approach to another, or is it time for a paradigm shift with a solution similar to Native RPC? So the solution of Native RPC is all about relying on the programming language itself. Imagine defining these 3 classes in TypeScript or Python. We define service as an abstract interface. We implement the class myService, and then we use service user to talk to myService in 3 different ways, either via an interface pointer, or directly with the class pointer, or remotely where the communication is being routed through a TCP/IP communication. All the message classes and all the services are being defined natively in whatever language you are using, making the remote communication indistinguishable from local usage. So what are the benefits of such an approach? Other solutions are busy dealing with custom schema definitions, custom remote API usage, and custom error handling. Native RPC circumvents many of these concerns by relying on the programming language itself. It requires some minimal boilerplate code to establish the communication and provides easy tooling for system monitoring and debugging. Otherwise, it relies on language-specific declarations for both messages and interfaces, and continues to use exception-based error handling. So this brings us to today's agenda. The next 3 slides will be all about building a distributed system from scratch. We'll be using programming languages such as Python, TypeScript, and C++, and we'll be defining a simple hello world service with 2 methods. Heya will accept dynamic dictionary payload and respond with the same, while hello will receive a formal statically typed message class and respond with the same. First, we start with an empty workspace in VS Code, which only has a single script for configuring the workspace. I will go ahead and start init. The idea here is to configure a workspace that looks like this. Native RPC folder will be git cloned from GitHub, and we'll create 3 boilerplate projects, 3 servers in different languages and 3 clients in different languages. At the end, we will execute a CLI tool called Native RPC, we'll call native RPC need to populate a workspace specific configuration. Just to take a look what the script is doing. So native RPC part is just doing git clone, installing Node.js packages, compiling Python binaries and C++ DLLs. Okay, next we come to, which is printed here. We're installing a virtual environment to fetch all the dependencies locally. In the requirements.txt, we define a dependency on native RPC folder, and it's being fetched into side packages stored locally. Next, we reach the TypeScript project section, which is doing npm init, creates a package JSON, adds a dependency on native RPC, and creates some dummy files. So package project refers to .native RPC, populates node modules based on dependencies, and so on. And the final step in the initialization is C++ projects, which defines a CMake list, some boilerplate CMake configuration that the main command is add executable, which is configured to compile main CPP. And the compilation happens into the build folder. We can see main it's already been generated. And the final step is native RPC init, which says that 6 projects found, updated configuration, workspace JSON. So once the workspace is fully configured, we'll define some interfaces and messages inside common files across different projects. Just a heads up, there's going to be some code duplication, which can be addressed later with some fancy code generation tooling. But for now, let's just define 3 interfaces in 3 different languages. Next, we need to define the message class in all 3 languages. And finally, let's add one extra class called inner, just to test composition of types. We will also copy these classes to the clients. Now we can finally validate what we have done with native RPC tool. So files is showing that we have 6 projects. These are the project definitions, and these are the schema definitions, and these are the services and messages being exposed. Native RPC types is showing that service called service has 2 methods with these parameters, and 6 out of 6 projects are defining it identically. Same for the inner and message. Once the native RPC types have been defined for every application, we get count 6 out of 6. It's time to define main applications. So there's going to be 3 clients and 3 servers. Let's let's start with the server in Python. So what we have done here is defined my service in 3 different applications. The Python code will return a field with value 1, TypeScript value 2, and C++ value 3. Same for the statically typed result. And one will listen on port 9001, then 9002, and 9003. The only difference is that in C++ you don't need to execute the main manually. Okay, now let's also define the clients. So for the clients, we used Native RPC client in all 3 cases and configured them to use correct host and the port and the service type. We also needed to execute connect, which creates a statically typed instance of the service. So we can start calling heya and hello. Finally, that we have all the services, messages, and clients defined, we can start executing things. I pre-copied all these commands in the 6 terminals. And let's do final sanity check with files and types. All types seem to be in check. No projects define correct number of services and messages. Native RPC PS stands for processes, -F stands for follow. It's following 3 different socket ports. So let's execute all 3 servers. This is how long they have been active. Next, let's start all the clients. So the clients are sending heya and hello at 1 second interval and printing out the result that the server has provided. So all the Python responses are 1, all the TypeScript are 2, and C++ 3. If I stop all the clients, they become dark and then completely go away in 5 seconds. Stopping servers does the same. As a final summary to this presentation, let's review what we achieved today. So we had minimal overhead in terms of number of lines needed to expose the service and number of lines needed to connect the client. We didn't use any kind of custom schema definition, no class annotations. Native RPC supports full metadata and runtime introspection, as well as using native exception-based error handling. The schema is semi-centralized with composable and fully dynamic types. In theory, it supports different transport layers and different serialization methods. We also were able to inspect the workspace in terms of files and projects, and inspect the schema in terms of services, methods, and fields. There's also a dashboard for looking at executing processes and TCP/IP ports. And we introduced some new CLI tooling as well as relied on very well-established CLI tooling for other things. Things we'll meet is automatic schema synchronization, because in theory you don't need to define the same thing six times. You can also automatically synchronize things. In the next presentations, we'll also address serialization formats and transport layers, as well as process orchestration with a custom process launcher. Things I also would like to review is routing and load balancing, and maybe create some tutorial for side-by-side comparison to other well-established techniques. Thank you. Special thanks to Niels Norman for his modern JSON implementation in C++. Thanks.